All right, now that we know about one-to-one and onto, what those ideas mean, we can talk about something called an isomorphism. If we have a linear transformation that maps things in the domain of U into the codomain of V, then if the transformation T is both one-to-one and onto, then we say that the transformation is an isomorphism. Your book suggests that an additional requirement is that the transformation of a scalar times a vector plus another scalar times another vector is equal to this. In other words, that the transformation preserves both scalar multiplication and addition. But it's not so much a requirement as an outcome. This will happen if the transformation is an isomorphism. When this happens, though, we say that the domain and the codomain are isomorphic. U and V are isomorphic. If your transformation happens to be something that looks like the examples we were working on in the previous video, where the transformation is executed by multiplying an input vector from the left by a matrix, if that's the case, then it's really easy to test whether this transformation is an isomorphism, because all you have to do is check whether this matrix is made up of linearly independent columns and whether those columns span the codomain. If both of those things happen, then you can say that the transformation is an isomorphism and that the domain and the codomain are isomorphic. If, on the other hand, your transformation, let's do it this way, your transformation goes from R3 to P2, and it might look something like this, from R3 to P2, so I have ax squared plus bx plus c. Now I don't have to, that doesn't have to be my transformation. It could be that the transformation of the vector ABC maps to bx squared plus cx plus c, or ax squared plus ax plus a, or ax squared plus, I mean, any combination is possible, right? I've just chosen one somewhat arbitrarily to indicate what the transformation looks like. In this case, though, you can't test a matrix like we could here because there's no matrix involved. There's no matrix multiplying from the left by this vector from the left to produce this. It's some other transformation. So in this case, we kind of have to logic through whether or not the transformation is one-to-one or onto. So I'll take a look at one-to-one first, and that says for everything in the codomain, for every possible output that exists in the codomain V, that's going to be P2 in this case, I can only map that back to one thing in R3. I can only map it back to one input vector. If the number C is different here, then the number C is going to be different here. If the number B here is actually K, then it must have come from a case where the number in this position is also a K. So by sort of logicking through this, I would say this is one-to-one. Is it onto? That's another thing we have to check for. It's onto if every possible outcome here in the codomain, every possible polynomial of degree 2 or less gets used up in the application of all of the matrices in R3. And I would argue here that since these vectors, are made up of real numbers, and that A, B, and C can be any real number, right? Then, in fact, they could all be equal. So I even have that possibility. They can be zeros, so I have that possibility. Some of the terms are zero. Then I would argue that it is also onto, because everything in this, everything that looks like this, where A, B, and C are real numbers, gets applied, gets used up in, gets mapped to in the application of this transformation. So again, by logic, by argument, this is also onto, and therefore we can say T is an isomorphism. If one of those conditions is not met, then T is not an isomorphism. They both have to be true. All right, so now that we've established that T is an isomorphism, that R3 and P2 are isomorphic to one another, let's observe this other property that happens to fall out when we know that to be the case. I've selected two vectors in R3, and I'm calling them U and V, and I'm labeling them. I'm giving their components the same letter as their name, essentially, so that we know which one comes from which vector. And I'm saying A and B can be any two real numbers, any two numbers in the real numbers. Then the transformation of A times U plus B times V ends up looking like this. A times U plus B times V. Because we're just doing really basic vector scaling here inside the parentheses here, I'm just scaling this vector U by A and vector V by B. I'm going to get, still inside my parentheses here, I'm going to get AU1, AU2, AU3, and I'm going to cheat because you know me, I'm going to run out of room if I don't. I'm also scaling B, and then I'm adding the results. So I'm going to go ahead and add the results in here. So I have two steps in one. B, V1, B, V2, B, V3. I'll probably run out of room anyway. What does this transformation, T, do to anything? This is now a 3x1 vector, right? A 3x1 matrix or a three-dimensional vector. What does the transformation T do to a 3x1 vector? It takes the first component, which is A U1 plus B V1, and multiplies it by x squared. And then it adds that to the second component, multiplied by x, and adds the third component as a constant. And if I use the magic of algebra and distribute across here, I don't need to do that with here, with my constant term, I'll end up with, I'm going to reorder these as I go because, again, running out of room, AU1 x squared plus AU2 x plus AU3 plus, going back to this term, BV1 x squared plus BV2x plus BV3. And then if I factor out the A, I get AU1x squared plus U2x plus U3. If I factor out the B, I get V1x squared plus V2x plus V3. And again, ideally, I need one more step here. Let's see, can I squeeze it in up here maybe? And go up here and say that that is equal to A times, what is U, let's see my finger down here, U times x squared plus U2 times x plus U3. Well, that's what I would have got if I had just plugged this in, right? If this was U1, U2, U3, I would have got U1x squared plus plus U2x plus U3. That's what I would have gotten. So this right here is the transformation of the vector U. A times the transformation of the vector U. And the same thing is true down here. That's the transformation of the vector v. So what I've shown is that the transformation, where am I? The transformation of AU plus BV is equal to this, which is equal to this, which is equal to this, and so on. And that is equal to this, which means that, I'll highlight them. That way we have a record of it. It means that this thing right here is equal to this thing right here. And that's exactly what this statement right here says. So as it happens, if two collections of things, two sets, U and V in this case, R3 and P2 in this case, if they're isomorphic, then this statement will be true. There are some interesting and powerful results that come out of this, this statement here. That if two sets are isomorphic, if U and V are isomorphic, then this will be true. It turns out that you're not stuck with just two here. If I can do this with two, then I can take a third one and stick it in there as well. In other words, I could write AU plus BV plus CW plus DX plus, and so on, somewhat indefinitely, possibly indefinitely. I don't know. I'd have to think about that one. But I'm not stuck with just adding and scaling two vectors. The transformation, if these two spaces, if these two sets are isomorphic, then the transformation will preserve both addition and scalar multiplication at the same time. This holds true for more than just one input. And that's useful to know because if I choose for my, let me grab a highlighter. If I choose for my vectors, the basis vectors, then it turns out that the transformation of the basis vectors in U, take the basis vectors from U and transform them, you'll end up with you'll end up with, having done the transformation, the basis vectors for V. I should say a set of basis vectors in U produces a set of basis vectors in V. Okay. Another sort of outcome, if you will, is that the dimensions of both the domain and the codomain are the same. Well, that's evident here, right? The dimension here is 3. The dimension here is 2 plus 1 because we're in polynomials. So the dimensions are the same. That's another outcome of having an isomorphism. Those are both in theorem 6.3.2. I'm not going to prove that. I'm not going to spend a lot of time on it. It's a handy thing to know. I think one of the exercises asks you to explore that a little bit, but I'm not terribly sure, and I'm not sure that I really want to ask you to spend a ton of time on it. We don't need to know isomorphisms really, really well for this class. It's just kind of a nice thing to have a superficial understanding of. So an isomorphism preserves scalar multiplication, a combination of scalar multiplication and vector addition, right? It preserves that. It preserves bases. In other words, if you transform, if you know you have an isomorphism and you transform the bases, right, or a set of basis vectors from your domain, you'll end up with a set of basis vectors from your codomain. And you also know that the dimensions of the domain and the codomain are the same. So those are three nice things to fall out of a transformation which you know to be an isomorphism. Now, if you don't know that it's an isomorphism, then you can't say those things necessarily. But if you know that it's an isomorphism, then you can. Now, your textbook seems to be implying that in order to be an isomorphism, the linear combinations have to be preserved. And so in the exercises, I'm specifically looking at exercise 6.3.5 right now. The first thing they do in testing for whether their transformation is an isomorphism is they do this test for the preservation of linear combinations. But once they've done that, they turn around and check for one-to-one and onto, because those are the critical things necessary for a transformation to be an isomorphism. I think the reason that they do that is because it can be a relatively simple check. If a transformation is an isomorphism, then it's because it's one-to-one and onto. But it's also true that linear combinations will be preserved. If this transformation is an isomorphism, then this statement will be true. If this statement is not true, therefore, this cannot be an isomorphism. So one way to check whether it's an isomorphism is to make sure that this statement holds true. But this is not enough by itself. So once you've checked, plugged a couple of vectors in and checked to see whether the transformation, the way I did down here, because my linear combination is preserved, if I was checking to see whether this was an isomorphism, I should check this first, and if that fails, then I know it's not an isomorphism. If it succeeds, however, I'm not done. I have to go back in and check to see whether it's one-to-one and onto. Sometimes that's easier, sometimes this is easier. And in your textbook, they always seem to check this first, and then once they know this linear combinations are preserved, once they know that passes, they go back and check for one-to-one and onto. These are the critical things that make a transformation an isomorphism. Now, we've also talked about the preservation of bases, and we've also talked about the fact that an isomorphic transformation will have the same, the dimensions of its domain and codomain will be equal, right? So those are the two other sort of little pieces, and they're pretty big in your textbook, but I'm not going to ask you to do any of those exercises. The information that we have up to this point, just what is an isomorphism and how can you check for it? That's enough for us for this course. If you go into, if you end up taking abstract algebra as a mathematics major, for example, then you'll learn a lot more about isomorphisms and homomorphisms and automorphisms and all kinds of other fancy and wonderful things. But right now, for this class, this is really all we need.